Imagine you're sitting in your final Cambridge physics exam. You flip the page and you see this exact scenario. A person holds a 50-kilogram boulder perfectly still above their head for 2 minutes. State whether work is being done on the boulder and justify your answer. This is a classic trick question, and it completely destroys unprepared students. Let's look at two hypothetical students taking this paper. We'll call them Alex and Sam. Alex is a textbook memorizer. Alex writes a massive paragraph about muscle fatigue, chemical energy burning in the body, sweat, and gravity. Total overload of facts, zero analytical precision. Then there's Sam. Sam rushes. Sam just writes yes because he is using force to hold it up. Both Alex and Sam just scored absolute 0 marks on this question. Why? Because they fell into the trap of using everyday language instead of the strict, unbending rules of physics. In this explainer, we are going to train you like a samurai. Ancient warrior wisdom meets modern exam strategy. We're going to learn how to slice through Cambridge physics questions with absolute precision, starting with the fundamental concepts of work, energy, and power.
To master the paper, you have to separate everyday English from physics terminology. In normal life, holding that boulder feels like a ton of work. Your muscles are shaking, your heart is pounding. You say, "I'm working hard." But the Cambridge examiner doesn't care about your heart rate. In physics, vagueness is the absolute enemy. Physics redefines work with mathematical ruthlessness. For work to be done in a scientific sense, a force must actually move the point at which it acts in the exact direction of the force. Movement is non-negotiable. If there is no displacement, there is no work, period. So that boulder you were holding, because it wasn't moving, no scientific work was being done on it, no matter how much energy your body was burning. Sam missed the movement requirement, and Alex wasted time talking about biology instead of physics.
Today, we are building your ultimate physics success blueprint. We're diving deep into the Cambridge syllabus, specifically focusing on the core principles required for papers like 9702, 0625, and others. We are building a mental toolkit covering work, energy, and power. Think of these 3 concepts as the fundamental rules that govern everything in the universe, from a tiny child's toy being pulled on a string, all the way to a massive roller coaster plunging down a track. If you can master how these 3 interact, you can decode almost any mechanics question the examiners throw at you.
Here is our battle plan for this session. First, defining scientific work, where we decode the command words examiners use. Second, the currency of energy, where we'll look at how to structure your answers using the Peel framework: point, evidence, explanation, link. Third, power the speed of work, which includes an interactive workshop to test your eye for data. And fourth, potential versus kinetic energy, where we combine everything into a flawless final system.
Let's start slicing into Section 1, Defining Scientific Work. This is where force meets displacement, and it's where your exam strategy actually begins. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Seriously, getting these definitions right is step 1 to securing your grade.
When you see the command word define work done on a paper, this is exactly what the mark scheme is looking for. Work done equals force multiplied by displacement in the direction of the force. If you just write force times distance, you will lose the mark. It has to be displacement in the direction of the force. Let's say you're pushing a car. Pushing it horizontally down a road requires a certain amount of work. But lifting that exact same car vertically off its wheels, that requires vastly more work. Now remember your vector rules. Both force and displacement are vectors. They have a specific direction. But work itself? Work is a scalar quantity. It only has a magnitude. We measure this magnitude in joules. 1 joule of work is done when a force of exactly 1 Newton moves its point of application by exactly 1 meter in the direction of that force. Now here is where the examiners love to trap you. What happens when the force and the displacement aren't perfectly lined up? Look at this classic scenario: a small tugboat towing a massive ship. The ship is moving straight forward, horizontally, but the tugboat's towing rope is angled upwards. The question is all of the pulling force from that tugboat actually doing useful work to move the ship forward? The answer is no. If you just multiply the total tension in the rope by the distance moved, you've just failed the question. You have to resolve the vector. To get those green check marks from the examiner, you have to use trigonometry. Step 1, identify the total force and the actual displacement. Step 2, find the angle between them. Step 3, use the formula work equals F times X times the cosine of the angle. Let's practice rewriting a flawed answer right now. Imagine a child towing a toy car with a string at a 25-degree angle. The tension is 1.5 newtons. The student Sam writes work equals 1.5 times distance. Wrong. Only the horizontal component of that 1.5 newtons is actually doing the work of pulling the car forward. You have to calculate 1.5 multiplied by cosine 25. That gives you the effective forward force. Multiply that by the distance, and you get your exact work done. The vertical component of that pull? It does absolutely zero work because the toy isn't lifting off the floor. This is the level of precision you need.
Let's move to Section 2, the currency of energy. This is all about how systems store the ability to do work and how you explain this connection clearly to the examiner. If you are ever asked to define energy, keep it simple and sharp. Energy is the ability to do work. That's it. If you wind up a spring on a toy, you are applying a force over a distance. You are doing work on that spring. And by doing that work, you are actively storing energy inside the spring's coils. When you release it, the spring can now do work, like launching the toy across the desk. An object that has the capacity to do work must have energy. An object with zero energy is completely useless. It cannot do any work at all. Because work and energy are essentially two sides of the same coin, they are intimately connected, and both are measured in the exact same unit, joules. Remember this connection, because examiners love multi-part questions that make you calculate work done in Part A and then ask for the energy transferred in Part B. It's a free mark if you know they're the same value.
To truly understand this currency, you need to appreciate the mind-bending scale of energy in the universe. Cambridge occasionally tests your understanding of magnitudes. Look at this scale. A single human heartbeat uses about 1 joule of energy. Now look at the microscopic level. The radioactive decay of a single nucleus releases a tiny fraction of that, around 10 to the power of negative 13 joules. Now scale up massively. An earthquake releases 10 to the power of 19 joules. And the rotation of the entire Milky Way galaxy? An incomprehensible 10 to the power of 50 joules. But here's the genius of physics. Whether it's a decaying atom, your beating heart, or a spinning galaxy, it is all measured in the exact same universal currency of joules. Which brings us to the ultimate rule. If you see the command phrase, state the principle of conservation of energy, you must write this word for word. Energy cannot be created or destroyed. It can only be converted from one form to another. Don't deviate from this. When the news talks about a global energy crisis, mathematically speaking, they are wrong. The total energy in the universe is perfectly constant. What we are actually experiencing is a fuel crisis. Think about a car engine. It takes stored chemical energy and fuel and converts it into useful kinetic energy to move the car. But a massive percentage of that energy is converted into completely useless thermal energy, heat escaping into the air. When the car brakes, the kinetic energy becomes heat in the brake pads. The energy was never destroyed, it simply degraded into a form we can't use anymore. This law is why perpetual motion machines, those intricate, endlessly spinning wheels you see on YouTube that claim to generate free energy, are completely impossible. It is a massive trap. If an exam question asks why a machine eventually stops, the answer is always that energy is dissipated as heat due to friction or air resistance. Efficiency is just the ratio of useful energy out divided by total energy in. Because efficiency can absolutely never exceed 100%, you can never get something for nothing.
Moving to Section 3, power. This is where we introduce the element of time. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's look at how fast work gets done.
Welcome to the interactive workshop portion of the explainer. I'm going to put 60 seconds on the clock for this next segment, so stay sharp. First, the definition. Power is the rate of doing work, or the rate of converting energy. It answers one question: how fast are you spending your joules? The formula is power equals work done divided by time taken. P equals W over T. The unit of power is the watt. 1 watt simply means a working rate of exactly 1 joule per second. So a small 1 watt LED light bulb is converting 1 joule of electrical energy into heat and light every single second. Let's do a find the flaw challenge. Look at these two vehicles, a standard family car and a high-performance Grand Prix racing car. Suppose we put the exact same amount of chemical energy, fuel, into both. Student Alex writes, the racing car does more total work because it goes faster and is more powerful. Did you spot the flaw? The flaw is saying it does more total work. That's incorrect. Because they have the same amount of fuel, they do the exact same amount of total work. The difference is the racing car finishes the track way faster. Its engine is more powerful because it converts that same amount of chemical energy into kinetic energy at a much higher rate. Remember, a massive force that doesn't move, like our boulder, does zero work and therefore has zero power. Power requires action over time.
Now for a speed writing challenge. You have 30 seconds to derive the alternative power equation. Go! Okay, here's how you do it perfectly for the examiner. We know power equals work divided by time. We also know work equals force multiplied by distance. Substitute that in, power equals force times distance all divided by time. Now, what is distance divided by time? It's velocity, so substituting that, we get our final equation, power equals force multiplied by velocity, P equals Fv. If you know the driving force of an engine and the steady velocity of the vehicle, you instantly know its power output. This derivation is worth easy marks if you memorize the steps. Finally, we reach section 4, potential versus kinetic energy. This is where we bring motion and gravity into our final system. Look at this roller coaster paused right at the peak of its track. This is the ultimate visual summary of everything we've talked about. When the mechanical motor dragged those heavy cars up that massive incline, it did work against the force of gravity. That work didn't just vanish, it was banked, it was stored. The cars at the very top are absolutely brimming with gravitational potential energy, which is simply the energy possessed by a mass due to its height in a gravitational field. As the cars crest the hill and begin to drop, that stored potential energy doesn't disappear, it is violently and thrillingly converted directly into kinetic energy, the energy of motion. Here is your ultimate cheat sheet for calculating this exchange. We use two specific equations. For gravitational potential energy, the change in energy equals the mass of the object multiplied by the acceleration of freefall, which is generally 9.81 on Earth, multiplied by the change in height. Delta EP equals mg delta h. For the motion side, translational kinetic energy equals 1/2 times the mass times the velocity squared. EK equals half mv squared. As the roller coaster's height decreases, the mgh value drops. Simultaneously, as its speed increases, the half mv squared value rises perfectly to match it. Assuming no friction, it is a flawless mathematical one-to-one exchange rate. You can see this exact energy exchange rate being utilized in heavy industry all the time. Look at this massive pile driver. It is essentially a gigantic weight that a motor lifts high into the air. By doing work against gravity to lift it, the machine fills the weight with gravitational potential energy. When it's released, it plummets. Gravity violently accelerates the mass, trading its height for velocity. It trades potential energy for massive kinetic energy. When it finally slams into the metal piling on the ground, that huge amount of kinetic energy allows it to do an incredible amount of physical work in a fraction of a second, driving the steel deep into the earth. It is exactly the same physics as a hammer hitting a nail, just scaled up dynamically. We have built the complete system. We've mastered work, power, and the kinetic potential energy dance. Now, let's apply our 3 rules for top marks. Decode the command word, use the PEL framework, and manage your time. Let's look at this final Cambridge scenario. A 120-gram stone drops down a 9.5-meter well. What is its exact speed right before it hits the water? First, assume air resistance is negligible. That means all initial potential energy at the top will perfectly convert into kinetic energy at the bottom. Set the equations equal. mgh equals half mv squared. Notice something amazing. The mass m is on both sides. It cancels out entirely. You don't even need the 120 grams. You just calculate the square root of 2 times g times h. Plug in 9.81 and 9.5, and you get exactly 13.6 meters per second. That is the true power of physics, predicting the future of a moving object with total precision. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.